Welcome back, boys. Today we will start a new lesson, eighth chapter of the first textbook, Electromagnetic Waves. Electromagnetic waves. Okay, so in the first chapter, we learned about electric charges and electric fields. Okay, so a charge at rest produces electric field. We have learned it. When charge moves, we get current electricity, right? And we learned in moving charges, when current flows through a conductor or moving charges, produces a magnetic field. Now, when you come to electromagnetic induction, we saw that a varying magnetic field can produce an electric field. When magnetic flux linked with a circuit or coil changes, EMF is induced. We have learned. Okay. In this chapter, we are going to see that a varying electric field can produce a magnetic field. A varying electric field can produce a magnetic field. So in the previous chapter, we have seen a varying magnetic field produce a electric field. So in this chapter, we are going to see that how a varying electric field produce a magnetic field. Okay, actually this electric and magnetic fields, they are the two sides of the same coin. They are closely interrelated. They are symmetrical. These two fields are symmetrical. Okay, so we will learn this in this chapter, electromagnetic waves. So first topic in this lesson is displacement current. Okay, so this displacement current you are hearing for the first time, right? And we will learn how it is produced. This displacement current, it was discovered by Maxwell. Okay, we will see how displacement current is produced. So our chapter name is Electromagnetic Waves, chapter 8. Chapter 8, Electromagnetic Waves. So first topic is displacement current. So in the fourth chapter, we have learned Ampere's circuital law. What is Ampere's circuital law? Closed integral P dot dl is equal to mu0 times the current. Okay, this is Ampere's circuital law. There we consider a loop. Okay, so this is a circular loop you consider. This is an open surface, right? A current is passing through this, like this. Then closed integral P dot dl. This is known as line integral. B dot dl equals mu 0 times the current. This we learned in the fourth chapter. This is Ampere's circuital law. Okay. Now we consider a parallel plate capacitor. See, this is a parallel plate capacitor. Okay. Parallel plate capacitor. One side is, one plate is positive, another plate is negative. Suppose it is connected to a circuit like this. There is a current I. Now we are going to apply Ampere's circuital law at this point. You imagine a point P. So you consider a closed loop like this, circular loop. We are going to find the magnetic field at the point P. So you consider a closed loop. So there is an open surface. The plane of this circle is the open surface. Current is passing through it. Now we can apply Ampere's circuital law. Closed integral V dot dl is equal to mu 0 times I. Okay. So we can find out the magnetic field from this equation. V dot dl. This will be B into integral dl is 2 pi r. Mu 0 I. And you can find out the magnetic field. Mu 0 I by 2 pi r. So at the point B, there is a magnetic field. Now, you are considering a different loop or a different surface. That surface has a shape of a port. Okay. See, I'm drawing again like this. This is a parallel plate capacitor. Positive charges here. Negative charges on the other plate. Okay. And I am considering a port-shaped surface. See, this is the surface. See, it look like a port. You know, port. But this surface is not touching the capacitor plate. Remember, the surface is not touching the capacitor plates. When you apply Ampere's law through this circuit, what will be the Ampere's circuital law? Closed integral V dot dl equals mu 0 times I. Now you imagine the point P, same point like in the previous case. Now see, between the capacitor plate, there is no current. So closed integral B dot dl is equal to 0. Okay. Closed integral B dot dl equals 0. That means magnetic field is 0. Okay. So there is a contradiction. In the first case, we got a magnetic field at the point P. But in the second case, at the same point, magnetic field is 0. That means there is a contradiction in Ampere's circuital law. So Ampere's circuital law is not correct in both the two cases. Okay, there is a contradiction. If Ampere's circuital law is true, at the same point P, we should get the same magnetic field in both the cases. But we are not getting. Okay, at the point P, in the first case, there is a magnetic field. Second case, we consider another loop only for at the same point. Magnetic field is 0. So there is a contradiction. Okay. So at one point, P, we calculate the magnetic field using different loops, right? Or different surfaces. But we are getting not the same value. That means there is a contradiction in Ampere's circuital law. Why this contradiction? The reason for this contradiction is, see, we know that there is no current between the capacitor plates, because between the plates there is nothing, air only. Current cannot pass through. So there is no current that we consider like that. But there is a current there. But that current is not due to not the conduction current through the wire. There is a current between the capacitor plates due to the varying electric field. We did not consider that current. That is why it is coming zero. So between the plates of the capacitor also, there is a current. That current is due to the varying electric field. Okay. But remember, if electric field between the plates varies, then only there is a current. That current is known as displacement current. So what is displacement current? It is the current due to the time varying electric field. If you have a space and electric field in that space is varying, there will be a current. That current is displacement current. For such a displacement current, no need of a wire to flow through, right? It will be in the space only. So we did not consider that current. That is why Ampere's law is inconsistent. Okay, this was found by Maxwell. So there is a current between the capacitor plates that is known as displacement current, that is due to time varying electric. So Maxwell modified the Ampere's law. So he modified Ampere's law like this: closed integral V dot dl is equal to mu 0 times I. That is a normal current. I am writing IC, conduction current. Plus, there is one more current, ID. ID is called displacement current. So displacement current is due to the time varying electric field. If electric field is not varying, there is no displacement current. And displacement current and conduction current both are equal in magnitude. Conduction current is the current through the wires, conducting wires. Displacement is the current in space between the plates. These are equal. Both the currents obey Kirchhoff's laws. Okay. So what is displacement current? It is a current due to time varying electric field. And now we are going to find out the equation for displacement current. You know, capacitor plates, you learned in first chapter. There is an electric field between the plates. What is the electric field between the plates of a parallel plate capacitor? You learned Gauss's theorem application. Electric field between two plates, oppositely charged plates, sigma by epsilon 0. Okay. What is sigma? Q divided by A. So sigma is Q divided by A. That is E. Okay. So what is Q here? A epsilon 0 E. If you differentiate Q with respect to time, you will get a current. So dQ by dt. That is, differentiate that. D by dt of A epsilon 0 E is equal to A epsilon 0 into d by dt. This current is known as displacement current. Okay, this is known as displacement current, ID. So ID is equal to A epsilon 0 dE by dt. See the equation, A epsilon 0 into dE by dt. If electric field varying with the time, then only this current exists. If electric field is not varying, no displacement current. Okay. So this is the equation for displacement current. And we know, last chapter we assumed that a capacitor does not conduct DC. Why the capacitor does not conduct DC? When the capacitor is connected to a direct current battery. You can see that charges are there, but charges will not vary. Electric field is not varying. So displacement current is 0. So there is no current between the plates at steady state. When capacitor is connected to a battery at steady state, that means when the current through the battery becomes steady, it will not pass through capacitor, because steady current means electric field will not vary, charges will not vary. That is why a current through the circuit is 0. That is why capacitor does not conduct a direct current. But if the capacitor is connected to alternating current, you know the charge is varying continuously. So between the plates, there will be electric field. That is why there is a continuous current in the circuit. So conductor is, capacitor conducts alternating current. This is the reason. And I hope you understood why capacitor block DC. Because when the capacitor is connected to a direct current, you know, initially some current increases from 0 to maximum, then it will not change. Then electric field will not change. Then displacement current is 0, because no electric field is changing. That is why capacitor block DC. It cannot pass through. DC current cannot pass through capacitor. But AC means continuously charge is varying, electric field between the plates varying. That is why capacitor conducts AC. Okay, this is the concept of displacement current. Okay, this is very important. Okay, what is displacement current? It is a current due to the time varying electric field. What is conduction current? It is a flow of charges through conduction wire. For displacement current, there is no wire is needed. It exists in space, right? This topic is very important, and this is the reason behind the production of electromagnetic waves. Now we are going to learn how electromagnetic waves are produced.